Have you ever seen a picture of the sky filled with dancing, glowing curtains of green, of pink, of purple light? That incredible display is called the Aurora Borealis, or the Northern Lights. It's one of nature's most spectacular performances, a celestial ballet high above our heads. But this isn't magic. It's science. The aurora is a visible sign of a powerful connection between Earth and the Sun. It's a cosmic story with a beginning, a middle, and a truly dazzling end. We're going to explore it step by step. It all starts with the sun, much more than just a bright daytime light. Where can you get a front row seat? The name Northern Lights gives you a big clue. Auroras love the cold and cluster near the North Pole. This auroral zone includes Alaska, northern Canada, Iceland, Norway, Sweden, Finland. There's a southern twin, the Aurora Australis, the southern lights appearing near the South Pole, over Antarctica. To see the aurora you need a dark night, clear skies, and to get far from city lights. Best time: long winter nights, roughly September to April in the northern hemisphere. The longer the night, the more chances the lights will flicker and dance. Think of it like a movie theater. You can't watch with the house lights on. Deep winter darkness is the perfect black screen for the aurora's vibrant colors to pop. What are we actually seeing? The aurora is simply light. Tiny particles from the sun smash into gases in Earth's upper atmosphere. Imagine a giant planetary neon sign. A neon sign sends electricity through gas which glows a specific color. The aurora works similarly, but the energy comes from the sun, and the sign is our sky. This light show is a direct result of the sun's constant activity. Let's zoom out, way out, about 93 million miles, that's 150 million kilometers away from Earth, to our star, the Sun. The Sun might look like a calm, steady ball of light, but it's actually a super hot, incredibly active place. It's a giant ball of gas, mostly hydrogen helium. At its core, it's so hot and under so much pressure that it creates energy through a process called nuclear fusion. This energy radiates outward, giving us the light and heat we need to live. But the sun also has a bit of a temper. Sometimes it throws things out into space. The sun's surface is a churning, bubbling cauldron of superheated gas called plasma. Plasma is a special state of matter where atoms have been broken apart into smaller charged particles, positively charged ions, negatively charged electrons. This plasma is constantly moving, creating powerful magnetic fields that twist and stretch like giant rubber bands. Sometimes these magnetic field lines get so tangled up that they suddenly snap. When they snap, they release a tremendous burst of energy and send a massive cloud of charged plasma blasting out into space. This stream of charged particles flowing away from the sun is called the solar wind. It's not like the wind we feel on Earth that rustles the leaves on trees. Solar wind is a completely invisible, super fast flow of tiny particles, traveling at speeds of up to 1 million miles per hour or even faster. Think of the sun like a giant sprinkler, spraying these particles in all directions throughout our solar system. Earth, along with all the other planets, is constantly moving through this stream of solar wind. Sometimes the solar wind is a gentle breeze. Other times, after a big explosion on the sun called a solar flare, or a coronal mass ejection, it's more like a powerful hurricane. A CME is like a giant solar burp, flinging 1 billion tons of plasma into space. When a powerful CME is aimed at Earth, it means a much denser and faster-moving cloud of particles is heading our way. This is important because a stronger solar wind means there's a greater chance for a more spectacular and widespread aurora here on Earth. Now that these tiny charged particles have been launched from the sun, they begin their long journey across the vast emptiness of space. It's a cross-country road trip on a cosmic scale. Traveling at incredible speeds, these particles of the solar wind take anywhere from 1 to 4 days to travel the 93 million mile distance from the sun to our planet. During this time, they are just flying through the vacuum of space, a river of invisible energy flowing past planets, asteroids, comets. For most of this journey, there isn't much for them to interact with. Imagine you're one of these tiny particles, an electron, let's say. You were just minding your own business in the sun's hot atmosphere when, bam, a magnetic explosion shot you out into space. Now you're zipping along, part of a huge cloud of fellow particles. This cloud is what we call the solar wind. For days, you see nothing but the blackness of space, with the sun a blindingly bright star behind you, and the distant planets looking like tiny specks of light ahead. Your destination, though you don't know it, is a small blue and white marble in the distance, planet Earth. As this solar wind gets closer to Earth, it encounters something amazing, something that protects our planet from this constant bombardment of radiation. Earth isn't just a rock floating in space, it's a rock with a force field. This invisible shield is called the magnetosphere, and it's generated by the movement of molten iron deep inside Earth's core. Think of Earth as having a giant bar magnet stuck right through its center, with a North Pole and a South Pole. This creates a huge magnetic field that surrounds our entire planet. When the solar wind finally arrives at Earth, it can't just plow straight through. Instead, it crashes into our magnetic field. The magnetosphere acts like a shield on a spaceship, deflecting most of the solar wind around our planet. It protects our atmosphere from being stripped away and shields all life on the surface from harmful radiation. If we didn't have our magnetosphere, Earth would be a very different and much less friendly place. The solar wind would erode our atmosphere and life as we know it couldn't exist. So thank you, magnetosphere. So our planet's magnetic field is like a hero, saving us from the solar wind. But it doesn't block everything perfectly. The magnetic field lines, invisible pathways of magnetic force, loop out from the South Pole and curve all the way around to the North Pole. The field is strongest and most compressed on the sun-facing side. On the night side, the solar wind stretches the magnetosphere into a long tail, kind of like a windsock, or maybe a comet's tail. That's called the magnetotail. This is where things get really interesting. While most solar wind particles are deflected, some get captured by the magnetic field. They get funneled along magnetic field lines. Think of cosmic water slides for charged particles. Those slides guide particles toward the Earth's magnetic poles, North Pole, South Pole. The field lines plunge into the atmosphere in an oval ring around each pole. This is the auroral zone. Think of a funnel. The wide opening catches particles from the magnetotail. The narrow spout directs them into specific spots. Earth's magnetic field gathers particles from a huge area and concentrates them over the poles. That's why you can't see aurora from Florida or Hawaii. The particles are guided to the very top and bottom of the world, so you have to be near the poles to see the show they create. This capturing happens all the time, but it intensifies when a strong solar storm, like a CME, hits Earth. During a storm, the magnetosphere is squeezed and stretched, storing huge energy in the magnetotail. Eventually, that energy releases explosively, sending massive waves of particles down field lines to the poles. Then auroras become incredibly bright, fast-moving, and can be seen much farther south than usual. We followed the particles all the way from the sun across millions of miles of space, and down the magnetic water slides toward Earth's poles. Now, for the grand finale. As these high-energy particles, mostly electrons, are funneled down into the atmosphere they're moving at, like incredible speeds. They finally end their journey by crashing into the atoms and molecules of gas that make up Earth's upper atmosphere, mostly oxygen-nitrogen. This is where the light comes from. The collision is the final beautiful step. When one of these fast-moving solar particles hits an atom of gas in our atmosphere, it transfers some of its energy to that atom. This excites the atom, which is just a scientific way of saying it gives it a temporary energy boost. But the atom can't stay in this excited state for long to get back to normal. It has to release that extra energy. And how does it release it? By emitting a tiny particle of light, a photon. Like hitting a bell with a hammer. The bell rings to release energy. The atom rings by giving off light. Different gases at different altitudes make different colors. The most common color is ghostly green, produced when particles hit oxygen atoms around 60 to 150 miles up. Above about 150 miles, oxygen collisions can produce rare red auroras. Pinks and purples on the lower edge come from particles hitting nitrogen molecules at lower altitudes, around 60 miles up. So when you look up at the aurora, you're not just seeing pretty lights. You're witnessing billions and billions of individual collisions between particles from the sun and atoms in our atmosphere, all happening at once. The curtains of light are the visible result of a massive energy exchange between our star and our planet. It's a direct visual connection to the powerful forces that shape our solar system. The aurora reminds us we live on a dynamic planet in a dynamic universe, and that even 93 million miles away, the sun can reach out and paint our night sky with science. It's a truly awesome phenomenon.